Alright, welcome everybody. Today we're going to be continuing our conversation on some different measurement techniques. In the measurement module, talking a little bit about some of the technical thinking behind how we actually want to develop and measure a good lean system. So, as a quick follow-up from the intro of the previous section, there's kind of two key questions when we talk about the technical tools. When do we need them and what are they, which relate to tools to measure, tools to improve, this module and the next one. Then that of course correlates to having good understanding and developing good skills, which is what we're looking for in order to be able to affect a good lean transformation. So in this one, focusing again on tools to measure, this is section 2 of the module. And in this, there's kind of three things we're going to be talking about. Previous was the key point indicators, and in this section we're going to be talking kind of briefly about yield and defect rates. What they are, how we use them, and most importantly, how we think about them, because that's the key here. So first, we'll talk kind of quickly about yield and what it actually is. So really, the traditional thinking of yield is pretty simple. It's the amount of good product divided by the total product. So kind of an idea of how much was bad. So in this example, say we produce some amount of product off of an assembly line or a process or whatever it could be. We inspect it. If it's bad, some of it gets reworked, and then we ship everything that we can. So in this case, we make 100 units, only 75 of them pass inspection. We can rework 20 of them. So our sum total is we ship 95 units. We ship 95 good units to the customer. Now in a traditional thinking, that would yield us, no pun intended, that would give us a yield for this production line of 95%. Which is pretty good. I think everyone would be pretty happy if we could get that consistently. But what we really want to do, because we want to capture what's really going on and understand where our waste truly is, we kind of want to change the way we think about yield. And we want to use this idea of a first-time yield. And what that would look like is run through the same example, is that it's the good product minus the rework divided by the total product, right? We want to isolate that rework. And the reason we want to do that is because in this case, when we account for our rework, we find out that our first time yield, the amount of product that goes through correctly the first time, which is ideal, is really only 75%, which is substantially worse than that 95% we were patting ourselves on the back for. And the reason we want to isolate that rework is because we want to be able to identify the hidden factories within our facility. And that is what rework or scrap or cheating and having to work on something twice or assemble it 2 or 3 times to get it right. That rework, even though it still goes out the door as a good product, that's lost time, that's lost money, that's lost efficiency. And we don't want to cover it up with how we measure it, right? That's why we want to focus on first time yield, so we can really see what's happening. Then moving beyond kind of individual yield for just maybe one step or one process, we kind of want to look at how we find the yield of a whole system. If there's 9 links in that chain, how do we find that whole system yield so we can start making big picture comparisons? Well, we use something called rolled throughput yield, and really all that is, what that little formula means, is you just take that first time yield for each step and multiply them all together in one big chain. So in this case, we've got 1, 2, 3 steps right in a row. And we come up with that first time yield for each one of them. It's 85 in the example, 85% for step 1, 92% for step 2, he's doing a great job, and 87% for step 3. Now what the whole yield of the system would be, that rolled throughput yield, we just multiply all those together in a chain. And what we come up with is 68%. And the key takeaway here is this rolled throughput yield, RTY, what that represents is that's the percent chance of the entire system producing a correct part or a correct product or a correct end result the first time through. And that's what we want. In an ideal world, we want 100% of the time the entire system should produce a correct product start to finish the first time through. So calculating this rolled throughput yield now gives us a good baseline understanding of where we are compared to where we want to go, where that ideal is. And that's kind of the value of thinking about yield that way, thinking about it accurately. And the next thing we're going to talk about quickly is this idea of defect rates. Something everyone's familiar with. Everyone uses it in some form or fashion. The traditional way of thinking about that is this idea of defects per unit, which is pretty standard. You take the total amount of defects and you divide it by the total production quantity. But what we really want to do in lean thinking is we want to kind of shift the way we think about that. And instead of defects per unit, we want to think about it in terms of defects per opportunity, which is just the total number of defects divided by the total opportunity for defects. And we really want to think about, is DPO, defects per opportunity, is that more accurate? And probably one of the quickest examples to use for that is, say you have two individuals working side by side. One of them is building a bicycle with 100 parts. One of them is building a car with 15,000 parts. Now if we just measured defects per unit, and say the individual building the bicycle had 5 defects per unit, the person building the car had 100 defects per unit, would we say, the individual, the process that built that bike was substantially better? Well, if we were just looking at defects per unit, their numbers were better than the other numbers, so yes, we would. But now if we looked at defects for opportunity, if we truly looked at what was going on, well, 10 defects out of 50,000 opportunities is much better than 5 defects out of 50 opportunities, right? So thinking about this kind of smart and thinking about this in terms of what's really happening, understanding those hidden factories, things like that, lets us make smart decisions based off of the numbers that we've got, the data that we're collecting. We're really able to put things in perspective and understand what's happening much more effectively. That's the important takeaway out of this idea of defect rates and defect for opportunity. The last thing we're going to talk about kind of in terms of that is how we can compare these different defect rates from process to process, line to line, department to department, kind of etc. And really how we relate DPO, that defects per opportunity, to how capable a process is this idea of a sigma score. It's represented a lot of times just with the letter Z. And what that really is, the math behind it, and we talked a little bit about some of these numbers in the previous section, is it's really just the absolute value, that's the vertical bars, of whatever the specification limit is minus the average of what we're producing. So just for example, if the specification limit was, this part had to be from 5.8 inches to 6.2 inches, and our average was 6.1, it would be 6.2 divided by, or minus 6.1, right? That would be what the top was. And then the bottom is just our standard deviations, which is a simple, straightforward way to calculate. I'm not going to get into the formula for it here, but it's pretty simple. You can do it in Excel or any of those programs, calculator for you. It's pretty straightforward. But what that does, what that z-score really tells us, is how many standard deviations of our process as it sits right now, with what's coming out the end of it, the product we're making, that variation, how many standard deviations are going to fit within our specification limit. How tightly clustered are our results, and how close are those results to what our actual goal is. That's what that z-score is going to tell us. And we calculate it for both the short-term and the long-term variation. So we can see kind of just the naturally occurring day-to-day stuff, tolerances, things like that. How good is that score? And then the long-term is going to show us, the external things. Individuals were late, or line shift, or equipment going down, right? That type of stuff shows up in the long term to show, over a period of months or days or weeks, how good is our actual score in terms of defect rates. And that z-score is actually kind of the namesake of, well, not kind of, but it is the namesake of Six Sigma. So a z-score of 6, or 6 sigma, is 3.4 defects per million opportunities, right? That is ideal, not ideal, but that's near perfect quality if you can get a z-score of 6. But the real kind of takeaway here is, outside of that kind of footnote, is calculating and coming up with the z-score for our different processes actually lets us make really accurate comparisons about which ones are running better than other ones. So for instance, if we have 2 production lines, or we have 2 departments within an office, and one has a z-score of 3, the other has a z-score of 5, we know that the one with the higher score is doing something right. We can go see what's happening and maybe share some of the things that are working with the other one that's struggling. It's a good tool to measure so that we can kind of compare and see how we're doing, and also focus kind of our problem solving and our improvement activities too. If we think about it, we may think that one area is struggling pretty badly, but this gives us a nice way to understand what the data is actually telling us. So again, just like with everything else, we can be smart about how we're using our resources and making the improvements where we actually have the true business need. So that kind of covers that brief discussion just about yield and defect, which are two, not really to belie the importance of the concepts, because they're very important to think about and kind of think effectively, because using those appropriately really helps give a very accurate representation of the state of quality and the state of performance of the processes within an organization. So if there's any questions, kind of follow up for that, send them through the website, and we will see everybody for our next discussion. Thanks.